Circular motion describes an object moving along a circular path. This fundamental concept in physics appears everywhere around us, from planets orbiting the sun to cars turning corners. Here's a crucial insight. Even when an object moves at constant speed around a circle, its velocity is not constant. This is because velocity is a vector quantity that includes both magnitude and direction. Since the direction of velocity is constantly changing, there must be acceleration present. This acceleration is called centripetal acceleration, and it always points toward the center of the circular path. The force that causes this centripetal acceleration is called centripetal force. It's important to understand that this isn't a new type of force, but rather the net force that points toward the center of the circle. A common misconception is the idea of centrifugal force pushing objects outward. This is not a real force. When an object breaks free from circular motion, it simply continues in a straight line due to Newton's first law of inertia. Modern physics education has embraced technology to make circular motion concepts more accessible. Smartphone sensors like accelerometers and gyroscopes allow students to conduct precise experiments and visualize these principles in real time. Understanding circular motion requires grasping the relationship between speed, velocity, acceleration, and force. Remember, constant speed doesn't mean constant velocity. Changing velocity requires acceleration, and centripetal force is simply the net inward force that keeps objects moving in circles. Circular motion involves several key characteristics that define how objects move in circular paths. Understanding these parameters is essential for analyzing any circular motion scenario. The radius r is the distance from the center to any point on the circular path. Tangential speed v is how fast the object moves along the circle's edge. Period t is the time for one complete revolution, while frequency f is the number of revolutions per second. Angular displacement theta measures the angle covered, and angular velocity omega is the rate of angular change. Now let's examine the mathematical relationships that govern circular motion. These formulas help us calculate forces and accelerations in circular paths. Centripetal acceleration directed toward the center is calculated as v squared divided by r. This acceleration is what changes the direction of velocity in circular motion. Centripetal force, calculated as mass times v squared divided by r, is the net force that keeps objects moving in circular paths. This force always points toward the center of the circle. The relationship between linear and angular speed is given by v equals r times omega. This connects the speed along the circle's edge with the rate of angular rotation. Circular motion appears everywhere in our world, from the cosmic scale of planetary orbits to everyday rotating machinery. Let's explore some fascinating examples. Planets orbiting the sun demonstrate circular motion on a cosmic scale. Gravity provides the centripetal force that keeps planets in their orbital paths around the sun. Amusement park rides create thrilling experiences through circular motion. Riders experience centripetal acceleration as they move in circular paths, feeling forces that seem to push them outward. Circular motion appears in countless everyday applications. From spinning wheels and rotating machinery to computer hard drives and washing machines, these examples demonstrate the universal nature of circular motion principles. Understanding circular motion is vital across many fields. Engineers design rotating machinery and vehicles that turn safely. Astronomers study planetary and satellite orbits. Even in sports, athletes use circular motion principles in events like hammer throw and discus. Modern physics education continues to evolve, with new concept inventories being developed to better assess student understanding. These tools help identify and address common misconceptions, ensuring students develop a deeper grasp of circular motion principles.